My talk today is focused on why 5D and 6D sensing, and is 4D not enough? So in the case of 4D radar, today I'm introducing a new terminology, which is the point vector cloud. The Oxford RF solution is to use 4 sensors only, not 8. All 4 of them will have a 270-degree coverage. We provide at least bifocal coverage all around the vehicles. Hi, good afternoon. I'm Kashif from Oxford RF. We design radar sensors, and in fact, today we are doing a product launch, which is quite exciting for us. We are industry leaders in providing the widest field of view available in the market. So specifically, we do solid-state 360-degree sensing, which means that we sense the full 360 degrees in one solid-state package. And we are the only company in the world which has this capability. Other sensors which you will see in the market can do 360 degrees, but they have a spinning or rotating component inside them. LiDARs, for example, they will have spinning optics. Radars have spinning antennas. So we have a patented antenna technology which allows the full 360 degrees beamforming without any moving parts, which means that our sensors are more reliable, they have a longer life, they're more precise. Today I'm launching 3 product series. One is our H360, which gives full 360-degree sensing capability without any moving parts. The second is our A270-degree series, which is the automotive radar version. This is at prototype stage, and obviously we are happy to conduct the trials. And specifically, we can use this to enable 5D and 6D sensing, which I will talk about. And then the third is our DX100 series. So the DX100 series takes the solid-state 360 sensing to the next level. I mean, you could probably wonder, what is the next level? So the next level is that we can sense not only the full 360 around the sensor, but also we can give a dome-shaped coverage. So this can be useful in applications where, say, an industrial vehicle needs to sense the 360 degrees around itself, plus it needs to know the height of the roof, and there are lots of applications. For example, this is really good for drone-mounted applications where the drone needs to sense around itself, and then it also needs a measure of the altitude from the ground. So obviously these 3 products, we also have a stand outside. If you want to have more information, we'll be really happy to speak to you, and we love collaborations and trials. So essentially, what we are doing is that our sensing technology is the next level. So we've combined spinning sensors, which can ordinarily do 360 degrees, but mechanical parts inside them, and solid-state panel sensors. They can look in one quadrant or one direction, and but ours obviously can do the full 360 without any moving parts. And this allows us to offer the sensor at a lower cost point than any 360 sensor in the market. And it has enhanced durability. There's no servicing required, so mechanical parts, they need servicing. And obviously it has a reduced environmental impact as well, in terms of not only the power consumption, which comes with mechanical motion, or if you're stacking multiple sensors to get the full 360, it will consume more power. And there's no audible noise in this as well. So for example, the 360 sensors, they have an audible noise with them. So my talk today is focused on why 5D and 6D sensing, and is 4D not enough? So 4D sensors are common in the market now. If I remember correctly, they started to enter the market in Q1 2020. So they haven't been around for long. So 4D sensors give the range and velocity information, but I will build on that in a little bit. So the central question which I want to ask is, what is the role of a sensing system? And the answer to that is that a sensing system senses the environment. So the environment, as we can see, can have pedestrians, cars, multiple objects. And a sensing system needs to output the kinematics of those objects in the environment. Now, the kinematics include the position, the velocity, which has three components to it, and the acceleration. And so the sensing system itself will have the perception sensor, which will be the front end gathering the data, and then it will have a compute engine, which will include estimation, tracking, AI. The key thing, especially for this talk, is that perception sensors are fast, and the compute engine takes time. It takes energy and obviously resources, it's costly, et cetera, et cetera. However, the biggest thing is that it takes time to process the data and then output a decision, which is the key point. So the question really is, how much of the kinematic information is coming directly from a sensor? And how much of it do we need to deduce by running a lot of algorithms on it? This is the central question. So if there's less information coming from the sensor, then the compute needs to work harder, and that takes time, which means that the driving decision is slower. 2D perception sensors, like cameras, they will produce the X and Z picture of the environment, and then the perception processor needs to work really hard to understand the rest of the kinematics. 3D LiDAR, high resolution, yes, but it's still positional data. The point cloud is only position information, really important. So obviously the perception engine needs to work to work out the velocity and the acceleration. 4D perception sensors, there's lots of them, including ours, which is displayed outside. So they will compute the position, the 3D position of an object, and one component of its velocity, which is along the road, right? And this is something that is not emphasized on clearly, and obviously I'll build on that. So the perception engine needs to take that data and work hard to compute the remaining kinematics. And that's where a 5D sensor can help. So a 5D sensor will output 3 components of the position and 2 components of the velocity, which means that it will tell you the velocity along the road, and it will tell you the velocity across the road, which means that you can characterize fast dynamics without any algorithms. And that's the beauty of it. And so I've quickly done this case study. So this is a lane change case study. So how fast can an ADAS system detect this maneuver? So a 2D or 3D system will produce a point cloud, which is effectively points representing every object. And I think everybody in this room knows about the point cloud. And the point cloud basically moves from one lane to the other. The key point here is that we have to combine multiple frames of data to understand that maneuver, purely because it was a 2D or 3D point cloud. Those dots didn't have an arrow with them. I'm going in that direction. No, the dot is a circle. It can go in any direction. So the only way you can know that this maneuver is going to happen is if you combine multiple frames of data, which is where the time comes in. Okay, so what happens in the case of 4D radar? So in the case of 4D radar, today I'm introducing a new terminology, which is the point vector cloud. So point cloud, everybody knows. The point vector cloud gives more information about objects in the scene. The points show the position, the vectors will show the velocity. So 4D radar is outputting the dots, which is the position, and then it's outputting the velocity in the direction of the car. And all is good. But when the maneuver happens, there's a problem here. Does anyone want to have a go at what the problem is?
Velocity vector.
The velocity vector. What should it do? It shouldn't be straight, absolutely. And that's the problem with 4D radar. Probably I'm the only one in the world saying this right now, but that's the problem with 4D radar. It only gives you one component of velocity. Velocity, as we know from fundamental physics, basic physics, has 3 components. So if you have 3 components of position and 3 components of velocity, then that should be a 6D sensor, right? So 4D radars output only 3 components of position and 1 component of velocity. Specifically, 4D radars cannot measure the lateral movement of objects in the scene. So a 5D radar will actually give you that information. And that's the importance of this, which means that we no longer need multiple frames of data to estimate these maneuvers. So how do we do 5D and 6D sensing? Here's two examples of it. So essentially, we can do this by combining multiple 4D radar sensors. And so there's the option number one, which has two conventional 4D radar sensors installed in the two corners of the vehicle, looking in the front direction. Looking in the front direction, and then you can combine their information. However, we can see there is a problem, which is that we need to make a trade-off between the coverage and the overlap. So if the radars are overlapping more, then they have holes in their coverage. So, and similarly, there's option number two, which is on the right side. So on the right side, we've actually colored it as well. So we can see the region of no coverage, region where one sensor is covering, which is the monostatic region, a region where more than like two sensors is covering, that's the bistatic region. But even in the right side, you see that there is a trade-off between how accurately you can place these sensors. And there's 8 sensors. So the Oxford RF solution is to use 4 sensors only, not 8. So all 4 of them will have a 270-degree coverage. We can provide that today. This is not a science fiction or anything. So 270-degree coverage on the left radar, 270-degree coverage on the right radar. So their coverage overlaps. So not only do we need only 4 sensors to cover the full 360, but there is a good overlap, which leads to a picture like this. So we provide at least bifocal coverage all around the vehicle. So, and there's trifocal coverage in most of the space. So there's going to be the strip, which is just the length and width of the car, which is bifocal at the moment. But the remaining complete space is trifocal. And the other, so we'll quickly go through this, is that this architecture is really well suited to a central ADAS architecture. So specifically, we can take the data, and the front ends, we are making them really like they're just producing the data, no processing at all in them. So the heavy lifting can be done by the central ADAS ECU. And then the other important point is that this is a very scalable architecture. So for an entry-level car, you can use a low-cost ECU. And for a high-end car, you can use like a heavy ECU, and you can do all the neural networks. And obviously, from that perspective, the same architecture is very scalable, can be used for entry-level to advanced vehicles. And hence, at Oxford RF, multiple sensors does not mean more sensors. Last of all, our product line. So we have a stand. Do please visit us. So thank you so much.